All right, well, welcome everyone. Thanks for making it out. And I really appreciate those of you who trekked back and forth across campus. Um, we were supposed to be in a building across campus and just found out on Monday that they were not going to let us be in that building. I may have noticed that campus is closed. This is a holiday, so campus is actually closed today. But we were insistent we were going to do this event anyway, so they gave us this room. But I'm afraid I apologize for the confusion there. That was a surprise. Um, Welcome. My name is Brian Jackson. For those of you who have never attended one of these events, this is the First Friday Astronomy event. I teach physics and astronomy here, actually in this very room. This is one of our lecture halls. These are monthly lecture series that take place on the first Friday of every month. Picked that because it was alliterative and easy to remember. And these happen all through the year. So 12 months of the year, even on a holiday, we'll host these events. We will hopefully be in the LART building for the next one. That's where we're intending to be, is in the LART building, because it's got a much nicer lecture hall. So if you want to come down to campus, that's probably where we'll be going forward. We also live stream these. And so if you want to watch this at home in the comfort of your own home, you can watch it on YouTube. I think you can just probably do a YouTube search, Boise State Astronomy, and this will come right up. But if you want to keep informed about events in the astronomy program, we have a newsletter you can sign up for right outside on the table. We do not spam. I think it's once a semester you get a newsletter, and that's all. So it's not too much. So yeah, these programs take place on the first Friday of every month. We've got a really great lineup of speakers booked, locked down for this coming fall, because this fall is actually the 10th anniversary of this program. So we've been doing this for 10 years. It's really hard to believe that. But 10 years. And so we booked some really superstar speakers. Not that all of our speakers aren't superstars, but some we really tried to reach high for the fall. And so we've got some really fun events coming up in the fall. We'll probably have some fun giveaways and things like that. So keep tuned to that. And I would suggest signing up for our newsletter so you can learn about that. One of the efforts that has been supported by folks who attend these events regularly is the observatory Reverb. So you may know there's an observatory on campus right across the plaza on the education building. It's been up there since 1978. It's still these original domes. The original dome, it could use some updating. We've updated it here now over the summer. We're just about done with that. And so we're hoping that our very first Friday Astronomy event in the fall semester will involve a visit to the observatory. So stay tuned for that. That should be a lot of fun. Other really exciting news this year, as of yesterday, literally yesterday, the physics department is now the physics and astronomy department at Boise State. Yeah, so that was really exciting. So that's a name change, but it's it can be a big thing. So stay tuned for that. That should be a lot of that's a pretty neat event. We also I think next month these will be available. We have just finished designing and sent to the printers our 2027 astrophotography calendar. This is the third year we've done these, and they really have just gotten better and better every year. These calendars are chock full of photos that our students and our partners in our outreach program have taken. So almost all of these are pictures taken by our astronomy students, many of them in the Dark Sky Reserve in central Idaho. So they're just absolutely gorgeous pictures. I think these are going to go on sale next month. Like I said, we just sent them to the printer. They'll be available at the bookstore, and we'll also sell them here at the First Friday event. And I think there'll be an online portal where you can order them as well. So stay tuned for that. That should be a lot of fun. I'm really excited about that. And so with that, I want to, oh yes, and I should say all of this public event, a lot of this public programming, especially the First Friday events, these are donor supported. So if you think these programs are really great and you really want to help out, please consider donating. All of the money we use to bring in speakers and put them up, feed them food, that all comes from you all. So thank you very much for that. And please let us keep doing that, doing the astronomy that I know we all love. Okay, so with that, I really want to welcome our speaker for tonight. This is a real pleasure. We don't get to do this very often. Dr. Kirk Long is a newly minted PhD from the Astrophysical and Planetary Sciences program at the University of Colorado at Boulder. He did a bachelor's degree in science in physics in this very department. So he's one of our alumni. So he's one of our Rockstar alumni. He's going to go on, now that he's just finished his PhD, he's going to go on to a very prestigious fellowship in the Kavli Institute. Joint. Are you going to say what the letters stand for, Kirk? Kavli Institute for Astronomy and Astrophysics postdoctoral fellow, which is a joint appointment between Peking University and Garking University. So he's going to be back and forth between Germany and China. That should be a lot of fun. So he's done some really cool research that he's going to tell you about tonight on black holes. And so with that, let's welcome Dr. Kirk Long.
Hello. Thanks. Good. Okay. Thank you, Brian. Yeah, it's very exciting to be back here. I haven't really come back that often, to the chagrin of my mother, since leaving to go do my PhD. So it's a fun chance to come back and give a talk here about my PhD research, which I'm excited to tell you about. And the theme of this talk is how to weigh a supermassive black hole. That's what I've spent the last 6 years trying to figure out. I'm going to be telling you about a specific kind of supermassive black hole that resides within quasars. But before we get into that, I'd like to take you back in time and imagine. There we go. The universe as we knew it 100 years ago. So 100 years ago, the year was, say, maybe 115 years ago. We had the 19 teens, and relativity was hot off the presses. You may have heard of that. And that was where the first real mathematical formalism for what a black hole might be came from. So actually, a year after relativity was first published, Karl Schwarzschild, who was a medic in the battlefield of World War I, when he was sick in the hospital, he got bored, and he found the first exact solution to general relativity. So general relativity is it's a complex set of nonlinear partial differential equations, but you can solve it exactly in a few cases analytically. And what Karl Schwarzschild derived, which is shown here, was the first general solution for this that implied that maybe black holes existed. And what this describes is a metric where you have a universe that's filled with one blob of stuff that's infinitely concentrated, and it's not doing anything else. So it's a very simple universe model. But you'll notice that, even if you're not super good at math, you don't have to know differential equations. You can see that there's a potential problem in this equation that was immediately apparent. If you go on your calculator app on your phone and you try to type any number and divide by 0, it will complain, right? And so this was readily apparent to Schwarzschild and Einstein, but at the time they thought, this is not a real thing. This is just a quirk in the math. And it was not really postulated that these things would actually exist. Also at the time, just for context of what we knew about the universe, the Andromeda Nebula first became the Andromeda Galaxy. So we didn't actually know about other galaxies outside of our own Milky Way until around this time. And this is a famous plot from Edwin Hubble's observations, where he found the var means the star is variable. And using calculations done by Henrietta Swan-Leavitt at Harvard, he was able to figure out that what was previously known as the Andromeda Nebula was actually really far away, much farther away than anything else in the Milky Way. And so instead of just being kind of a nebula of stars in our own galaxy, it became its own distinct cluster out in the universe. And that was the first time we knew that there was another galaxy out there. And that's just 100 years ago. And now we know from Hubble also that when he was doing this work, he found many other galaxies. And he came up with this thing called Hubble's law, which you may have heard of. This is basically proof, another surprising thing that Einstein thought was wrong in his math, but turned out to be true, that the universe is expanding. And basically what Hubble found, as is just kind of shown simply in this plot here, is that the farther away you look, the faster things are going from you. And it happens isotropically in every direction in the universe, and that implies that everything is moving apart from everything else. So this is a lot of stuff was happening 100 years ago. And just to kind of show you also a funny thing about the specifics of how science evolves, nowadays we present this picture very neatly. When I learned about this in undergrad, it was presented very neatly to me. Makes a lot of sense. But this is like a plot of what's called the Hubble constant, which essentially parameterizes how fast the universe is expanding. And this is it over time. And you can see that when Edwin Hubble originally made these measurements, he actually did a terrible job. It's like an order of magnitude bigger than all of the current estimates today. And so back then, he would have thought, it turns out you can kind of flip this number. If you invert this number, you get the like 0th order estimate for the age of the universe. And he would have thought that the universe was like 10% of the value that the universe we know today is. He would have thought it was only like 1 billion years old instead of, say, 15 billion years old around, right? So fun historical aside. But this talk is about black holes. So I'd like to briefly introduce you to black holes. So we have this universe dividing by 0 thing. And if you plot this metric, you can see that it kind of acts, a black hole kind of acts like a waterfall in space. And so here we have this nice picture showing how space-time folds in on itself towards the singularity. And this is for that same solution described there. But I have a question for you. Do you think that the universe and real black holes are modeled well by just a single point that's doing nothing else? No. Yeah, that's a good thing. So it turns out that we can make this equation a bit more complicated. And I'd like you to think about what else at a minimum you should have to add to this universe for a second. Anybody have any idea? We know black holes, when they form from stars, we know that it's an explosion of the star, right, that then collapses in on itself. This is how they're born astrophysically. And when things collapse, what do they usually do? Who's watched the Winter Olympics? They move, and then they move in what way? Think about the Winter Olympics. Yeah, you have angular momentum. That's the fancy physics way for saying you're going to spin really fast. Okay, if you watch the figure skaters go, right, they start with their hands out here. And when they tuck their hands in, they spin really fast, right? And so we think that this solution for relativity is incomplete for that exact reason. It's not spinning very fast. And so it turns out, though, that while this one was relatively easy, it took Schwarzschild only about a year to derive this exact solution. To derive a universe where it's exactly the same as this, except it's spinning, took 50 more years. And it looks like this. Okay, so you get a little bit more complicated, where the spin parameter is called A here. It's dimensionless between 0 and 1. And this is now what a real kind of the coordinates of what we think astrophysical black holes are best approximated by. And so you can see this is already more complicated than maybe the simple picture that you've probably heard about. It turns out when you make things spin, instead of falling to a single point, this is, I think, a really cool, fun science fact about black holes. Instead of falling to a single point, you actually fall to a ring. So there's a ring-like singularity in the center of the black hole. And there's actually 2 event horizons when you make it more complicated like this. There's this thing called the ergosphere, where you can be, it's kind of like a false horizon that you can be inside of. Anyway, very cool. I'm going to stop there about this, but I'll just plug that my favorite job when I was an undergrad here was I worked at the Bruno Dunes State Park Observatory. Raise your hand if you've been there. Did any of you ever hear me talk there? No. You? Yeah. So that was a long time ago. But I'm gonna go there tomorrow, and I'll be running the telescope again for old time's sake and giving another lecture about more, the pop sciencey bits of black holes instead of the research bits of black holes. So if you're interested in that and you don't have 4th of July plans, you want to see space fireworks, you can join us out there. Okay. There's 2 kinds of black holes in the universe, though. So this is another thing that I feel like is sometimes lost in popular science, is that there are 2 distinct populations that exist in our universe. On the right is a picture of the sun in blue because it looks cool. And that's one way we can make black holes, not actually from stars the size of our sun, but from really big stars. You can collapse them and form a black hole. But the black hole that's left over at the end of that is maybe a few solar masses in size. It's not very large. And so we also know that there's the second population of black holes called supermassive black holes. And we found them residing at the centers of pretty much every galaxy except for some dwarf galaxies. But every like kind of big real galaxy, sorry to the dwarf galaxies, has a giant supermassive black hole residing in its center. And we're not actually sure yet how the two pathways are linked. So that was they asked me to write a question. And I said you have to say yes or no if the tiny black holes make the big black hole. And we don't actually know yet. So you could put whatever you want and you'll be right in some superposition of results of the universe. But the nicest picture, and I think the standard picture for a long time, was that the tiny black holes do make the big black holes. We just didn't know how. But I'll tell you a bit later that some results that we're seeing with JWST are starting to challenge this actually assumption. And so these two different regimes of black holes may indeed have distinct formation mechanisms that are intricately tied to how galaxies formed and evolved across cosmic time. I'm going to be talking about supermassive black holes. And so I'm going to be telling you about galaxies, the galaxy flavor of black holes. And I'm going to tell you about the first black hole we ever discovered. I'm going to give you a little history detour one more time. So the first quasar, the most famous and well-studied quasar, is called 3C273. Astronomers are really imaginative at naming things, as I'm sure you know. But these letters do mean something. So the 3C means that it was the third Cambridge survey. So at the time, back in the day, it was really easy to get a PhD because you could just look at the sky in like a new color of light. You could call that a day. You write down what you found. We've since mapped most of the colors of the sky. It's becoming harder and harder to find a new color to look at in the sky. But at the time, right at the end of the Second World War, there was there were a bunch of British engineers that had surplus radio equipment that they had used as radars for German planes and missiles, etc. And they had thought, well, what if we designed a radio telescope? This hasn't really been done at scale before. Let's look in the radio, see what's out there. And at the time, we knew about the Big Bang, so we knew that there was a cosmic microwave background that persisted, but we didn't really think there was anything else interesting to see in the radio. It was hypothesized that the sky would just be kind of, I don't know, like you would see the Milky Way glowing in radio because it has some hot gas and plasma helps make radio waves. But it wasn't really theorized that you'd see anything else except for the Big Bang kind of residual glow and then some, shadow of the Milky Way. But when they did this, they immediately found a bunch of sources in really weird places. So they found an isotropic distribution of radio sources all around the sky. And in this third Cambridge survey, one of the brightest sources that they found was the 273rd thing observed. That's how we get this name. And it was located out of the galaxy, clearly outside of the galaxy. So we didn't know what it was. And what I'm showing you now, though, this is a modern plot of where 3C273 is. It's inside of Virgo. You probably have heard of that before. And this bar represents kind of the original uncertainty with this crappy radio telescope. So very cool experiment, but it's hard to tell. You could see many things are underneath this bar. So we could see that there was radio emission coming from there, but we couldn't tell what thing was actually making the radio waves. We just knew it was kind of in this general area of the sky. Luckily, because it's in Virgo, some early astronomers, Martin Schmidt in the radio, and then Cyril Hazard in the radio, and Martin Schmidt in the optical, they collaborated because they knew that right after this was discovered, it was fortuitously forecasted that the moon was going to basically go straight through here. Because this is very near the ecliptic, so all the planets, when you look up in the night sky, all the planets are roughly in the ecliptic, and the moon is also in the ecliptic. And this meant that you could use the moon to occult this radio source and try to really narrow down the positions precisely. And so in 1967, that's exactly what they did. They watched the moon do this. Voila. And now they really knew where it was. But when they looked at it, they found something really strange. So Martin Schmidt took, at the time, the largest optical telescope in the world, the Palomar Observatory, so 200-inch telescope. And also, this was the largest radio telescope in Australia at the time. And supposedly, to get the observations, Cyril Hazard had to manually override the safety limits of the telescope. And the dish was borderline dragging on the ground, and he hit a tree or something. Anyway, so you could do, I don't think the NSF would let you do that these days with our new telescopes. But anything went back in the Wild West. And what he saw in the radio was really interesting. They saw that there were definitely actually two components in the radio, which is kind of strange. And then when Martin Schmidt took a picture, he saw that there was this bright star and then this annoying, I don't know, line. And at the time, they thought this line was probably just some galaxy that they hadn't discovered yet, some type of galaxy they hadn't discovered yet. And then they thought that this star was a star. And so they wanted to see, to confirm what the line was, to confirm that it was like, they thought it was like an edge-on spiral galaxy. That would look like a line in a picture. And so to confirm that that's what it was, they took spectra. So spectra is where we split up light into many different colors to tell what things are made out of. My favorite high school chemistry lab was where you lit stuff on fire and you got to see it glow different colors. This is just the fancier version of that we can do in space. And so on the top, obscured by these captions, is the spectra for 3C273. And on the bottom is a spectra of our sun. And galaxy spectra look roughly like a lot of suns combined together. And you can see that they don't look anything alike. Okay, so something really strange was going on. And it turned out that it wasn't a star at all. And so this is actually where the name quasar comes from. It originally stood for quasi-stellar radio source, basically, because they looked like stars when you took a picture of them, but we didn't really know. They clearly weren't stars when you took this spectra of them, when you tried to decompose them into the light. And eventually, a few years later, this was a mystery for some time, but in the early 70s, they figured out that if you pegged these emission lines to a ratio, the same ratio of about 1.16, you could shift them from where they should be on Earth. And that means that, and they were all shifted by the exact same amount. And that tells you that this source was redshifted towards us. And if you remember Hubble's distance ladder thing that Hubble figured out, they then were able to figure out how far away this thing was. So they could tell it was moving really fast away from us. 0.16 is pretty fast. And that meant that it was actually really, really far away from us. And so that's how we became to know that quasars were actually the first kind of confirmation that black holes existed in the universe. This velocity is about 50,000 kilometers a second. It's really fast, moving away from us. That means that it's a distance of almost 2 billion light years from us. At the time when this was discovered, it shattered the records. At this point in time, we knew that there were other galaxies, but we didn't know anything past a few 50 million light years away. So this was a record-shattering observation, again, that kind of expanded our cosmic horizon to 2 billion light years away. It was the farthest known object at the time it was observed. And it was figured out that that spiky thing was not some random galaxy, but in fact, a jet being launched from this really bright central supermassive black hole. And to prove to you that there's a galaxy underneath that bright spot, this is a Hubble picture. And Hubble has this nice thing called a coronagraph, which can block out the really bright black hole in the middle. And what you see surrounding that really bright black hole when we block it out is kind of the fuzzy, distinct signature of a galaxy. So it turns out that these are galaxies, but their centers are extremely luminous. And at the distance implied by the redshift, it turns out the luminosity needs to be like 4 times 10 to the 12, the luminosity of the sun, which is, for context, about 100 times as luminous as the Milky Way galaxy or any other normal galaxy. So just the central engine is 100 times brighter than an entire galaxy's worth of stuff. And that was the first proof that these were probably supermassive black holes. The only way we know of in the universe to make that much energy is to drop something really far. Turns out that's more efficient than nuclear fusion. If you just drop something, the gravitational energy that's liberated is a lot. And if you could drop something into a black hole, that's the best you could drop anything into. And so you're going to liberate almost all the energy possible from that object. And that's how you can power these jets and how you can power this extraordinary luminosity. That's quasar 3C273. Now, I'm going to tell you why we care about studying quasars to shift gears a little bit. Yes, they are supermassive black holes. It's the first confirmation of a black hole really existing observationally. So we went from 19 teens thinking maybe black holes existed in the math to 60 years later confirming that there really is an observational strong candidate for it. But why do we care about it besides that? Well, it turns out that black holes really set a lot of properties about their host galaxies beyond what they should. So I know black holes, they sound crazy. They're these massive objects. You think they should have this crazy amount of influence, but they're actually small compared to galaxies. Even the really big ones are small compared to galaxies. And so beyond a few parsecs, the typical galaxy is maybe like 100,000 parsecs across. And beyond a few tens of parsecs, the black hole should not really matter anymore. Its gravitational influence falls off to basically being nothing. For comparison, it's about a typical, like in our Milky Way, the black hole at the center of our Milky Way, it's 1/50,000th basically the mass of the Milky Way. So there's 50,000 times more stuff in the Milky Way in just the stars and planets and us than there is in the black hole in the middle. And so but it's been observed that black holes, the bigger the black hole at the center of the galaxy, the larger the galaxy itself is. Maybe that's because they grow at the same time. But also black holes appear to set a lot of other galaxy properties. They set how the stars are formed, even really far away. We see this observationally. They set how galaxies evolve, how their metallicities change across cosmic time. And so we really think that like the reason, maybe life is probable where we are in the Milky Way is because of our distance to our black hole and how our galaxy has grown with our supermassive black hole at the center. So it's really important for us to understand these black holes so that we can better understand how we got here and how the universe has grown and evolved across cosmic time. And black holes are cool because unlike a galaxy, which is super complicated, there's so many things you could say about a galaxy, right? There's a lot of stuff in there. Black holes, there's only two things you can say about them, okay? You can tell, we talked about this earlier, you can tell how big they are, number one, mass, and what's the second thing, do you remember? How fast they're spinning. All right, you can know nothing else about a black hole. How big they are and how fast they're spinning. And it turns out how fast they're spinning, like that's cool, but doesn't really matter to the large scale features. And so really we only care about how big they are. And that's where we observe all the trends with galaxy properties. We observe that how big the black hole is what sets a lot of what changes about a galaxy. So I'm going to teach you how we weigh a black hole. I have a PhD, but it turns out that all of the math that I learned in this classroom when I was like 18 or whatever. So raise your hand if you've taken like high school or very introductory physics at some point in your life. Like most of this room. So you'd be able to follow this. You remember this one? Yeah, you've seen this one before, right? F equals ma. All right, that's a good one. Have you seen this one before? Yeah, okay. So if we assume that gravity is the thing that's most acting on something, we set ma equal to Newton's universal law of gravitation. You can do some slashing on the little m's, do some rearranging. You can say that the acceleration you feel from a gravitational body in terms of Isaac Newton's parameterization of the universe is just gm over r squared. This should look familiar if you did take a physics class a long time ago. No worries. Now, let's take another simple assumption, because astronomers, we love to just ignore. So we can make the simplest assumption, which is to say that, let's say you're in a gravitational potential and you're spinning. That seems cool. And if you were to do that, you could follow the formula for centripetal acceleration. You've probably seen this before. It's v squared over r. So you set our a's equal to each other again. And voila, you do some canceling. You rearrange. And you can get that the mass of your object is equal to the radius times the velocity squared divided by g. That's a very simple formula. That is basically how we measure the masses of supermassive black holes and the masses of pretty much anything. If you've ever heard of how big an exoplanet is, it's this. Anytime you want to measure the mass of anything, you just have to find something spinning around it relatively close by, measure a distance and measure a velocity. Of course, we do want to make one further complication, which is what if the orbit is not a perfect like edge-on circle, okay? Or what if you have a bunch of stuff orbiting to make this velocity and you can't see the individual particles? Then you just you add what I've heard described as the fudge factor. So you change this equation, you just put a little f in front, and you say that could be any number you want, and the rest should be still the same as it was in physics 1. So not a very complicated relationship. And you might be wondering, well, Kirk, you just said that you had to solve these really complicated equations to figure out what a black hole is. Why don't you have to use relativity? relativity is like so cool, but it only matters like basically 10 times the black hole's radius away from the black hole. As soon as you're further than 10 times the radius of the black hole away, it doesn't matter anymore. You can just go back to this. That's why most of our lives, we don't, all the planets in the solar system basically follow Newton's law of gravitation. You have to measure things extremely precisely to find relativistic effects. So we have this recipe to measure the mass of a black hole. It turns out the hard challenge is actually not in the math, but finding these numbers in green and in orange, okay? And the orange brown one is easy to find, actually, kind of. So if we look back at our spectrum of, say, 3C273, this quasar, one thing that you'll notice is that the emission lines are extremely broad. This was a hallmark that was first noticed in them. When we looked at these emission lines, we had never seen emission lines that were that broad before. And there are a few different physical mechanisms that can make emission lines broader, but none of them could do it properly, except if you had something spinning really fast. Okay, so the idea here is that the widths of these lines, if you convert it into a velocity, which you can do with this formula here, it implies that there's gas orbiting around 2% the speed of light. That's 2% sounds like a small number, but the speed of light is like a really big number. So that's exceedingly fast, much faster than a human has ever gone or probably ever will go. And so this gives us a proxy for the characteristic velocity scale in these quasars. And this is one of the reasons that quasars are so important, is because they have this signature in their spectra. We cannot do this with most galaxies or most other sources because they don't show us this feature. So this feature is an observational hallmark of quasars that allows us uniquely to measure their masses. Now, you can do that with just one spectra, and we call where this gas comes from. Yeah, these captions are annoying. It's good for reading, but we call the region where these broad lines come from the broadline region. Really good at naming things. We call it also the BLR. And measuring R in this equation is a little bit more complicated for that reason. There's a really elegant physics experiment here that I'm going to show you that how we measure this. When we watch these things vary over time, it turns out that not only do quasars have these extremely broad emission lines, but they vary. They're always changing. They're changing their width. They're changing their brightness. You can watch them change on timescales of like days. It's really very cool. And what was noticed was that one part of the spectrum, what we call the continuum, which we think comes from very close to the central supermassive black hole from the accretion disk, if that goes up, 5 days later, the emission line will also go up. And if it goes down, 5 days later, the emission line will also go down. So this is kind of summarized in this picture, this movie here from Caltech, if it plays, which is that, say, the black hole burps, then a little bit later, you see it reprocessed outside farther away. And if you assume that basically you could calculate that distance, then assuming that it just took the speed of light travel time for it to go out there and do this effect, if that makes sense. And when we calculate this, that gives us a proxy for this R. What does that look like in practice? It's not as pretty as this schematic. This is not a real movie. We can't make these real pictures, unfortunately. But we do something called reverberation mapping. So this is like how a bat would see a black hole, basically. It's kind of like sound waves echoing off, but in space. And what's seen in the top panel is the continuum. Well, these two top panels are both kind of continuum measurements. And what's seen in the bottom 3 panels are the emission line measurements. And if you squint really closely, you could maybe say that, like, look, there was a peak here, and then a bit later, there's a peak in this one by like a tiny bit different. But we have computers and statistics that can calculate this for us. And we can do this in 2 ways. The first is with a 1D measurement. And so that's where we do it across the entire emission line. So we'd look at that whole broad emission line, and we just look as a whole, how does it go up and down? And that's what's shown in this plot here. And so if you see these these are called cross correlation functions. And you can see that they all peak. This is 0 delay, this tick here. So they all peak at some number bigger than 0. Okay, so when you try to line these things up, there's some number bigger than 0 that's causing this thing to happen. But we can also do it, and those are the lines to guide your eyes of approximately the right number of days, like to go from one peak to the next. And we can also do this in 2D, though. And this is what's really cool. Some recent experiments, which I'm going to talk to you about, have started to do this in 2 dimensions. where instead of just watching as the whole line goes up and down, they watch the line in chunks. And they see like, does like the left side of it go up faster than the right side of it? And that can tell us really interesting things about the structure. That's where we really get to like bat sonar levels of understanding the broadline region. Okay, it's another bad title. Why we want to do this? Why do you care about this? Well, you have to care about space and galaxies, but assuming you a priori you care about that, the scaling relationships, like how the black hole depends on the other properties of the galaxy, or how the black hole influences the other properties of the galaxy, they are anchored and derived from quasars at any distance that's outside of our local universe. So if you care about how the universe has changed and evolved across cosmic time, you need to do this measurement accurately, precisely, and at a lot of different epochs across the universe. So it's really important, really important that we do this. What does this look like in like plot form? Well, this is an example scaling relationship that's shown for the BLR. And what I want you to notice is basically on the y-axis is the time delay, and on the x-axis is how bright the thing is. And what this means is that brighter black holes have farther away BLRs. But the big thing that you want to notice about this is that there's a significant amount of scatter in this plot. So we're not doing it that precisely at the moment. And this matters because I don't know if you've seen this in the news, but with JWST, there's all these things coming out about like, the universe is broken. We found like a black hole that's too big, or we found the galaxy too early, right? Or something like this. You've probably seen some sensationalized headline like that. Those are mostly wrong. But there is a real problem in that in the question that I asked you at the beginning. This plot, the black points are all the measured masses of the farthest away galaxies. Importantly, all of the masses on this plot come from this scaling relationship on the right. So if we're not doing the scaling relationship on the right properly, all of the masses on the plot on the left are wrong. Okay? But what these people are saying in this paper, and this is what led to one of the sensationalized headlines, is that if you look at these lines, these lines are like predicted, like if you go back to the very beginning of time, when the universe formed and you made a black hole, how could it have grown to become what it is out here when you see it? Okay, this is like t equals 0 of the universe, and then this is when we're seeing it, about 1 billion years into the universe's history. And what they argue in this paper is that all these points are like underneath this line. So it's telling us that we need a more massive, and in fact, if you get into this regime, DCBH means direct collapse black hole. That means it's not possible for that black hole to have grown from a star that exploded. It had to have formed in some other exotic way. But this is only true if we've measured the mass properly. So it's really important that we measure the mass properly, because that will tell us how black holes grow and evolve from the very beginning of the universe until now. And I'll just say, I was at a conference this week where I saw a new result that came out like last week, literally, where one of my colleagues was trying to say basically that this relationship is probably overestimated. And he made a replot of this just to say that the universe isn't broken. And you can see that if you change this relationship, even just by a little bit, basically, by changing how you process the data, you can get everything to work again with, say, normal stars at the beginning of the universe. It still may be hard. You see some of these plots are still underneath the line, but the tension is much less. Okay. Now I want to tell you about another exceedingly cool instrument that we use to measure supermassive black holes. This is called gravity. So I'm going to be spending the next 4 years working with. It's the gravity telescope. It's on the VLTI in Chile. It combines all 4 of the big telescopes in the Andes, in the desert there. And the idea here, we use gravity, we use interferometry to try to make a bigger telescope out of the smaller telescopes. You're probably familiar with this. We made the black hole picture, if you've seen that way, right? We combine telescopes all over the world. This is the same principle, except we're not using radio waves, we're using infrared light. But it turns out that even when you combine all of the fanciest telescopes in the world into the gravity instrument, you get something like you could resolve something on the scale of milli-arcseconds. This is much smaller than a grain of sand on the sky. It's a very small thing. But it turns out that even the most nearby BLRs, for example, the broadline region in 3C273, is probably like, 10 micro-arcseconds, which is still a factor of 10 at least too small to be seen directly. We can't take a picture of the broadline region, even with our most fantastical telescopes. But fortunately, even before you can take a picture, you can know the center of a picture. This is a very cool calculus thing. So if you've ever done a Taylor expansion, this is what we're doing with this instrument. And the idea here that I'll just show graphically to you, the math is kind of complicated, but to show you graphically, this is a photo of me. I had much shorter hair. The PhD does, I don't know, things to you, but I've plotted on here, there are 3 circles. There's a blue circle, a green circle, and a red circle. That's the center of light of this image in those 3 different colors. RGB channels are what makes up an image. And you can see the red is drawn down because my shorts are kind of red in this picture. And the blue is drawn up because the backdrop is blue. And the green's kind of like right in the middle, as you would expect. And what I'm going to do is I'm going to make this picture really blurry. Maybe. And you can see that when I make it really blurry, you can no longer tell what the picture is. You have no idea that it's me standing next to, what is the mascot's name? Buster? I never went to a football game. I'm sorry. But you can tell that it's no longer me standing next to Buster Bronco, but what has been conserved is the positions of those 3 circles. Okay? And this is essentially what we're doing with gravity, but in space across the emission line of the broadline region. So here I'll show you the same technique, but now applied across the emission line. So you imagine that broad emission line. We take these snapshots in channels across the emission line, and we find the center of light in that specific channel. And when we scan across it, it looks like this. This is the raw data, and then I've kind of plotted those on this plot here. And you'll notice that all the blue stuff's on one side, all the red stuff's on another side. Any physics people know what that means? Yeah, and so what is one side doing? What's the other side doing? So what does that tell you? It's spinning. Yeah, that's what we want. We want to find something spinning, right? That's awesome. Okay, so we built this, multi-billion euro instrument in the Chilean mountains, and we can detect something spinning at a really remarkable scale, far away in the universe, more than 2 billion light years away. Okay, and so you can then kind of measure a size from this as well. So you can tell that it's spinning from the red and the blue, and then you can measure a size kind of plotted as that line across the points of how big the scale should be. And this is really powerful because you can just do this in like one night of observing. Whereas the other way, you have to watch for it to echo. You have to watch it for like a year, maybe 10 years, depending on the source. Okay. I'm just going to show you, we've recently upgraded this instrument. I'm going to go work on my postdoc. This is a super cool movie that they made to celebrate the Gravity Plus upgrade. It shows you these telescopes in the Chilean desert, rendered in Ultra 4K HD. And the big upgrade that we recently did is we put lasers on them. And we put lasers on them because we want to make artificial stars. If you make a laser, you can make an artificial star. You shine the sodium laser up. It hits the sodium layer in the atmosphere, and it bounces down. And you know exactly how bright it is and the height that it's at. We then pass that through a really fancy, complicated series of optics. The Germans really know how to build stuff and how to make cool movies. And we combine the light from all 4 telescopes together through a very complicated beam splitter. Yeah. And then we end up at the end, and this is just to show you why we want to do this laser bit, is that all these images come together, and at first they look really blurry. But then watch what happens to the mirror. Whoa. Okay, so we can track precisely. We know that these artificial stars that we made are not really varying like that. And so then we compensate for how they vary, and we move the mirror really fast like this, and it makes the image of the sky exceedingly crisp. And this is going to allow us to measure a lot of these sources much farther away than we were doing before. So now we know how to weigh a black hole. We get this delta V with the velocity, and we get this R from reverberation, or more recently with the Gravity Plus instrument. Okay, what else is left to do? Well, we care about this, as I said before, because we want to constrain. Basically, we have this chicken and egg problem is another thing about this. We have a chicken and egg problem. We don't know what came first, the black hole or the galaxy. And so we want to be able to do this at really far distances, because if we can catch a black hole being formed before the galaxy's formed, if we can catch it deviating from this scaling relation, then we'll know that the black hole came first. But if we can't catch black holes in the act of doing this, then we'll know that the galaxy came first. We can better tell our story of cosmic origins. And we can better characterize galaxies everywhere in the universe. We have these scaling relationships, and the one on the right is from the reverberation mapping, the echo thing, and the one on the left is from gravity. And you can see that right now we only have like 6 sources with gravity, because the original instrument, you had to pick targets very carefully. But now with the lasers, we're going to do it. We just had a very large program accepted that's going to start next year, and we're going to do it for hundreds of objects at all redshifts. I'll show you a cool one at the end of the talk. Okay, but to really measure the mass of the BLR, we have to understand this last annoying bit in this equation, this F factor. This is called the Vero factor, or as I like to call it, the fudge factor. And here I'm showing you is 2 different models of the broadline region that produces this gas in the context of AGN in general. And really, you don't need to pay too much attention to them, except that they're both versions in the literature. And you might ask, why do you have to do that? You know, like, why do you even need to make a model? Why can't you just measure it directly? And that's because the spectra is single peaked. So if you look at this line profile, it makes 1 peak. And this is an annoying complication that requires a model. And just to show you how bad the models are currently, this plot shows you what people think the value of F could be. And this is in log, which means it's 10 to this power. So it could be 0.1 or it could be 10. Okay? So there's a large amount of uncertainty lurking in our measurements just based on how we're modeling these sources and if we're doing it right or not. And to understand why this single peak is a problem and why a disk doesn't work, I'm going to take you through some cool animations that are very pretty. Or at least I think so. If you don't like them, then you don't have to tell me. The first is, let's imagine you had like a ball of gas and you wanted to make it spin. The ball of gas might start with a line profile that looks like this. And as you made it spin, it would look like this. Now, of course, this depends on how you're looking at it. We're looking at an edge on. If we were to tilt this fake thing down, it would collapse back to 0, right? If you're looking at it top down, we don't see anything spinning towards or away from us. But what if we cut a hole out in it? We could make it like a record player of gas. If we spin that up, you'll notice immediately there's a problem. There are now 2 peaks in this thing, which is not what we see in our spectra. But there's even a bigger problem, which is that gas in the universe doesn't spin on a record player turntable. It spins because of gravity. So if we add gravity to it and we make it, say, the mass of a supermassive black hole, is a really big problem. Okay, we're missing a lot of flux from the middle. So this is why originally, you can see that doesn't match the observations of the shape of the line profile at all. This is what originally motivated both of those kind of schematics of models that I'm showing in this thing here. And so we really want to get the modeling right because this F factor depends on it and our masses depend on it. So the key astrophysical questions, if we do this modeling properly, that we can answer are, I think, really important. Number one, how do galaxies and their black holes co-evolve across cosmic time? How do we get here, right? That's a fundamental question that we all, I think, want to know as humans. We could do that because our accurate models will give us precise mass measurements. And the second is just what's going on? What is the true nature of the stuff that surrounds black holes? We could really understand that. We're at the forefront of being able to understand that. If we have an accurate model, it'll tell us where the gas is. It'll tell us physics about the gas. That's really interesting. So I just want to show you like how these things change over time. This is a remarkable observational campaign that was done with the Hubble Space Telescope. They looked at one of these AGN, one of these quasars, for 180 days straight. They got the Hubble Space Telescope to take a picture every single day and a spectrum for every single day for 180 days. And this is how much it changes over 180 days. It's really fantastical that it changes this much. And you're able to calculate 2 properties from this, which is shown in the right panel. One in blue is the average kind of line profile, that broad single peak thing. And the other with the black points with the red line underneath, that's what I'm going to call the delay profile. So instead of one number for how long does it take for the gas to bounce off the other stuff farther away, they measured that number independently in channels across the emission line. What I really want you to notice is that the black points, there's 2 peaks in it, and the blue one has 1 peak. Okay? And it turns out that this was a key result of my thesis. I'm just telling you about the one key thing that basically I think that I found and contributed to science as part of my PhD. The biggest thing anyway is that this means that none of the models work. So if you look, this was a new measurement that was taken around the time I was starting my PhD, and I was tasked with interpreting it. And I was trying to model it under these existing prescriptions of kind of a thick disk or a thin disk, but with some kind of wind component. And the main thing that I want you to notice is that neither of them match both of the curves. Okay, they both look terrible. The blue one does a good job of the blue, but look at this red compared to that, right? That's terrible. And all of the masses that you see on the plot of the scaling relationship, they come from fitting this model in the literature. So who knows how wrong they are. And just to prove that I'm not pulling your leg, like the original people who took this data, they also fit it with their own version independently of me, of the cloud model. And you can see that you get this single peak in both things. And it's not unique to this one source. It's happening all over the universe. Here's a bunch of other examples of this where we've taken these measurements in the last few years, where there's these two peaks. So there's something really interesting going on. And kind of the key result of my thesis is that we're changing the picture of how we model these sources. And so we said to kind of explain them, we think we need some kind of hybrid model of the two. So the reason for that is that all the observers were telling me, when you see these two peaks in this delay profile thing, that means it's a disk. Two peaks equal disk from the animation that we saw earlier. But they weren't actually trying to fit models to it. It turns out you can't even get a disk to match just that. So they're really out of touch with how a simulation works, I guess. But it turns out that if you add a disk and you stack some of this puffed up stuff on top of it, you can get it to look much better. And that's what we showed in this paper. You can read it if you want. But the key idea here is that this is what we think the broadline region actually looks like. We're getting close to being able to fundamentally understand where the gas is and what it's doing. And so instead of these two pictures being the accurate picture of what these systems look like in real life, we think that it's maybe something more like this. And this makes a lot of sense naturally. In this model that we described, you have gas flowing in this disk from this outer edge of this torus. And then when it gets into the accretion disk, it puffs up. And it's being blown away by the extremely strong radiation pressure there. And those clouds end up being, those dark dots end up being concentrated there. So this is really exciting work. We're still in the process of actually fitting formally all of these things, but we think this is really the direction that we have to go. And certainly all the existing models are probably, people have to do something different. And this modeling is also really important in the case where gravity is not the only thing at play. So remember, we have this equation, right? This equation, it was derived under the assumption that gravity is what's causing the thing to spin. But it turns out this is not always the case. So what I'm showing you here is a really exciting, fresh, hot off the press result from the Gravity Plus instrument. And the main thing to notice is that the line profile has this kind of crazy skewedness. And then this phase measurement, it's only one-sided, which tells us that the gas is actually coming towards us, or at least significantly coming towards us. And so we have to fit an outflow to this model. And that means if you're having to fit an outflow to the model, you have to know what part is outflowing, what part is just spinning, because you need to only use the spinning part to get the mass, right? You need to ignore the outflowing part. And so we're going to really try to calibrate this at redshifts really far into the far universe. This is at a redshift of 4, which is really exciting because all of these other results are like 0.5 or less, maybe up to 1. So a redshift of 4 means the universe was less than 2 billion years old at the time when this source was doing this, and the light's traveled to us for a really long time. Okay, so kind of the key takeaways of this is that we have these scaling relationships, but there's a lot of uncertainty in our models that go into this, and we don't fully understand it. It probably matters because we want to tell the story of how black holes got to be where they are today and how they influence, the properties of galaxies as a whole. And then we can also just learn really cool things about how the system actually looks if we can model this properly. This is a cool animation showing different properties of the gas in this kind of combined model, if you're to believe that that's true. And then finally, maybe this holds the answer. Raise your hand if you've heard of like little red dots. Have you heard of this? Oh, wow. Yeah, okay, look this up. Yeah, these are really cool. This is a very new thing being discovered by JWST. Again, they're imaginatively named because they look in images like a little red dot. Okay, but they have broad lines, but they don't have the spectrum that we normally associate with AGN and quasars. And so we don't actually, there's a whole bunch of new theories that are being thrown out to try to explain them, and if we're really measuring the mass of supermassive black holes there. And I think that these kind of measurements will help us make that jump as well. So with that, I'll just leave up a nice conclusion slide with a bunch of other things I didn't talk about from my thesis, but that you could ask me about if you're curious, and I'll take any questions that you have.
All right, questions? Yeah, I have a million. I want to get a simple one.
Uh-huh.
How?
Yeah.
And I'm sure that's different, right? But we know LIGO hot to
Yes.
find
Yes.
them coming together.
It's true. So the question was asked like, we don't know how supermassive black holes formed, but LIGO is seeing black holes merge. So we definitely know that they do merge. And yes, it's true. We definitely know they do merge. A really important LIGO result from a few years ago was that they found what's called an intermediate mass black hole. If you think that the little black holes become the big black holes, there should also be some in between. But we've never seen the ones in between until there was a LIGO measurement that they've now found like 5 of them. It's still way too small a number, and all the ones they found are in the like less than 1,000 solar mass regime. You need to go from 1,000 solar masses to like 4 million solar masses. So how do you do that? We're still not sure. But yes, it is true that, I mean, either there are different mechanisms being proposed, and really the universe is messy. It's under no obligation to follow one set of nice rules. Maybe all the channels are happening, but we want to know which one is most important and which one's kind of dominant, especially at early times, and that's not clear yet.
So when you're taking like the spectra of the broad line and stuff, how can you make sure that you're not taking spectra of, let's say, like stuff you treated or?
Yeah. Yeah. The question was, how do you make sure when you take the spectra that you're taking the spectra of the right thing and not the wrong thing? This is a really important question. Yeah. A key thing that I kind of skipped over is that when we think about accretion disks, we know that one of the reasons we think that the continuum comes from the accretion disk is because accretion disks are really hot. And it turns out they're too hot to really form lines. So that's nice. If it's so hot, like at the center of the sun, for example, it's so hot that the atoms are all ionized. So they're not coming back together to make these emission lines. They're just trying to escape. Okay. And so the accretion disk doesn't recombine and make this hydrogen series of lines. And when we make the gravity measurement with the phase signatures, we're doing a similar thing actually, where we're basically comparing, we're not directly seeing the size. We're actually, one subtlety is that we're comparing the size in the emission line compared to the continuum. So it's again telling us like how far apart is the accretion disk from the broad line, similar to the reverberation experiment. And if those two were the same thing, you get an answer that was 0. But we get an answer that's not 0. So we can tell they're distinct components. Well, the key, so yeah, there's a question was like, what's up with the single peak versus the 2-peak thing? But the key like prediction of a spinning disk is that you should have 2 peaks. And the argument is that if you have a star, you should have 1 peak because it's a circle on the sky. But if you make it a disk, you cut out the middle. And when you cut out the middle, you cut out the middle of the light in the line, and you would get 2 peaks. But when we look at these things, we almost always see 1 peak. So we know that it can't just be a simple spinning disk. There has to be something at least a little bit more complicated than that. And that's the key motivation for all this modeling nonsense, is how do we explain, because we said at the beginning that the velocity is coming from the stuff spinning, but it's not making the structure that you would expect from the simplest possible spinning thing. So we need to model a more complicated spinning thing that can make the single peak, but still be spinning.
Would you dive into a black hole? Kirk? Would you want to go into
A supermassive one. Yeah, this is a good question I would always ask my students is, if you were going to jump into a black hole, should you go into a supermassive one or a stellar one?
Those are your only two options. Though.
You have to pick, yeah. Raise your hand for the stellar one. Raise your hand for the supermassive one. Yeah, I mean, I kind of gave it away. But the reason you'd want to go into the supermassive one is because you may have heard of spaghettification. Yeah. So the tidal stresses scale like the radius cubed. And so but the event horizon size goes like the radius squared. And so if you have a stellar mass black hole, when you fall in and you cross the event horizon, you're already really close to the middle, and so you're getting ripped apart immediately. No bueno. But the supermassive black holes, turns out, on average, this is a crazy fact, but like the supermassive black hole in the Andromeda galaxy, it has an average density of like water. Because it's extremely large. So we haven't been in a black hole. We don't know how the mass is distributed. It's probably distributed at the middle, and most of it's empty. But that tells you that it's safer to dive into the black hole in the Andromeda galaxy than it is to dive into the black hole that's formed from the star exploding next door. We could do some math on the board. I swear, look it up.
I had you were mentioning before, kind of on the date of the galaxies formed black hole.
Yeah.
And said that currently we don't know, like it hasn't been observed as to whether a galaxy is a black hole. So is it going to be continuous that we won't ever know its solution unless we see the galaxy forms from the black hole?
That's a great question.
If, like a black hole that never formed a galaxy figure out. Happen at some point over the universe.
That's true. So the question was like, will we ever be able to know the answer to this chicken and egg question? What came first, the black hole versus the galaxy? Just one more telescope, I swear, guys. Like, right? Like, but it turns out, so I didn't put this in the talk because there are nuances of this, but I'm very skeptical of the masses that people measure for supermassive black holes with JWST, because I think that there are many political reasons to get into about this, but they're probably right to like a factor of 10, but I think they could be wrong by like a factor of 10. Anyway, but what they're seeing is that already at the very earliest times, black holes are starting to deviate with JWST from the relationship that's expected of them, and the black holes are overmassive compared to what we think they should be. That implies that the black hole is coming first and is setting the properties. But this is a very tentative, like we're figuring this out like this year. So this story is actively changing and under review, and the JWST people, they also there's a real pressure for them to publish like immediately. And so they're often publishing things that are not fully vetted. And then there's an article that comes out about it in the news, and then a month later, they actually just did something wrong. Like they measured some part of the spectra wrong. And then they have to say, actually, it wasn't true, Yeah, but I think we will be able to tell that. If not with JWST, then with the upcoming extremely large telescope, we'll be able to make these kind of measurements for sure.
What's the all focus on quasar study?
Yeah, the question was, why do we care so much about quasars? What's the difference between them and normal black holes? Yeah, quasars are all supermassive black holes. So like our Milky Way has a supermassive black hole. It's not a quasar. That's good for us. Okay. If it was a quasar, it would be exceedingly energetic. There's one. Have you read about this? There's this one like hypothesis that one of the mass extinction events caused on Earth 2 billion years ago, I think the Ordovician extinction, was caused by our black hole having been a quasar for a brief moment in time, and the jet having been aimed at us. Yeah. Yeah. So, because that's one of the ones where they don't know what happened. That's like super speculative. There's not a ton of actual evidence for that, but that's just to tell you it's good. Our black hole is not a quasar, but supermassive black holes are quasars when they're actively eating stuff. That's important because that's what allows us to see them. They're only super bright because they're eating things. That stuff is falling in. Gravitational energy is being liberated. It powers these giant jets and these accretion disks. That's what allows us to see the broad lines. And then those broad lines are really important because that's what allows us to measure the mass of the black hole. So we can't do that for galaxies like the Milky Way that are farther away than like Andromeda-ish scales. We cannot measure their masses in any way. We have to rely on some other technique and then like map a scaling relation between them. So these quasars are really important because they anchor our scaling relationship. Anytime you look up a black hole mass online, your favorite black hole, you're on Wikipedia and it says it weighs this much, it probably was not directly measured, but comes from work that's influenced by these scaling relationships from quasars.
One last question, yeah.
So I was under the impression that they were able to by looking at
Yes, yeah. So the question is, can we measure the mass by looking at orbits of close stars? Yes, but only in a few very nearby galaxies. Like we can do this in our Milky Way. That's what determined the Milky Way was a black hole that won a Nobel Prize for Andre Ghez and Reinhard Genzel. We can do it in Andromeda. We can do it in a few other relatively nearby galaxies. But once you start going farther away than like 100 million light years, it's too small for us to see the stars in the middle, and we can't do this. And then we have to do this more indirect method. But yes, we can do that at the local universe.
Okay, let's thank Dr. Kirk Long.
We're gonna have a great presentation about meteorites being the storytellers of the solar system next month. So please join us for that. Thanks.